Good afternoon, everyone. Welcome to chemcamps, day 3. I know you had a wonderful time with Mrs. Elaine Williams on Wednesday and Mr. Imran Miller yesterday. Today is my turn to take you through organic chemistry. I'm a teacher at the St. Andreas School for Girls. I teach chemistry. I'm the head of the science department, and I coach the basketball team. And my favorite basketball player, of course, is LeBron James. And of course, anywhere he goes, I follow that team. So I used to be a Cleveland Cavaliers when he went to Miami. I went to Miami. Now he's back at Lakers. I'm a Laker fan. We played a game last night, and I was wondering if I would be able to do this session today if we had lost. So happily, we won that game. So I'm here and ready to go. All right. All right. So I have a lot to get through. Let me just give you a little background on what we're going to run through, and then we can start our session. Let me start here. So this is our syllabus. The organic section is a very large part of your syllabus. You have 3 sections, section A, section B, and section C. Section B, of course, covers sources of hydrocarbons compounds. We'll be looking at an introduction to organic chemistry. That's another big part. And then we'll go into reactions. But there are so many reactions. You have reactions of alkanes, alkenes, alcohol, carboxylic acids, which takes you into esters, saponification, and then polymers. I think I'll try to get through to maybe the 2 main reactions, which is alkanes and alkenes, if I can get to that. But the introduction section is very long, and it is the foundation for everything else. So I plan to spend most of the time there. All right, so you bear with me. So today we'll be looking at identifying gas and petroleum as natural sources of hydrocarbon. We'll be discussing the fractional distillation process of your crude oil, and then we'll discuss cracking before we go to the other section, which is the introduction. Any issues you have, you will put it in the chat, and our moderator, Dr. Francine Taylor Campbell, will assist with that. All right, so let us begin with our presentation. Just a minute. Let me just bring this up and start. All right, I'm going to close my video, but I'll be coming back on periodically. All right, thank you very much, and let us begin. All right, ladies and gentlemen, colleagues, all, we're looking at CSEC organic chemistry. Again, I am your facilitator, Franklin Burrell. Let me start by, of course, looking at the sources of hydrocarbon. And I want to walk you through a little video that will tell you how we get the petroleum from the microscopic animals and, well, the microscopic plants and animals, and then know where the natural gas come in, where is that coming from? And then now we look at the fractions. So let's start with a video. Pay attention. So if I ask any questions, you can answer.
What drives our cars, buses, and planes, powers our electricity, and allows us to cook our food and heat our water? Most of today's energy needs are met by fossil fuels like coal, oil, and gas. These unique, high-energy fuels are non-renewable resources that took millions of years to form. About 2 billion years ago, marine organisms like algae and microscopic animals and plants died and settled on the ocean floor. Beneath other sediments in the ocean, and in the absence of oxygen, these fossils changed into a substance called kerogen. Under heat and pressure, kerogen gradually changes into oil or gas. The whole process usually takes at least 1 million years. At the molecular level, oil and gas are hydrocarbons, made up of hydrogen and carbon atoms. The constant pressure and movement of the Earth's crust squeezes oil and gas through the pores or spaces within rocks. Some oil and gas reaches the Earth's surface and seeps out naturally into land or water. Often it is trapped beneath the surface by impermeable layers or rock structures, like faults and folds. Within the crust, oil or gas deposits build up and form reservoirs. Reservoirs are like vast sponges filled with oil and gas. They can be as large as a city. To find oil and gas deposits, geologists use a number of different survey techniques, including seismic surveys, gravitational surveys, and geological mapping. Seismic surveys use reflected sound waves to produce a 3D view of the Earth's interior.
All right, I think we can stop there. Just a minute, let me just make sure the sound is on when I share. I know you can hear me because of the microphone, but let me just share and turn on my sound from now. All right, here we go again. Yeah, good. All right, so basically, you just saw how we produced the crude oil. And when I say crude oil, you'll see here that your crude oil is your unrefined petroleum. Okay, so that is what we are looking at. You were told that hydrocarbons are made up of hydrogen and carbon. So we have two elements that made up the hydrocarbons. The petroleum is your naturally occurring oil, and we saw how that oil was produced. All right? Main points to focus on in the production of petroleum: the remains of microscopic plants and animals which lived millions of years ago. Now, if these microscopic plants and animals they died, of course, and then get covered under the ground or under the sea, under the earth, under the sea. And we know that that will cause the effects of high pressure and high temperature. So in simple terms, you are pretty much cooking the substances to produce the oil. And that is how we produce the petroleum. Now, when we produce petroleum, any liquids you have, any liquid, you will always produce vapor above that liquid. And the vapor that is produced above the liquid, here we call it natural gas. So let me show you a little diagram showing you your crude oil, which contain all the different fractions. And as you can see, this is your dark substance here, the oil. And above the oil is your natural gas. So if you want to extract the oil, you can. If you want to extract the natural gas to use, you can. And of course, the natural gas is a cheaper source of energy. Okay? Any questions so far?
Not yet. Students, remember to put your comments, questions in the chat and respond to Mr. Borrell. All right, go ahead.
Are we find out if everybody's following so far how we produce the oil and the natural gas, the two sources of hydrocarbons?
Okay, all right. No comments so far.
All right,
they're
good.
saying yes. They're saying yes.
All right, and it's clear how we produce the oil. All right, let's move on then. Now we want to separate now the crude oil into its different fractions. So we're going to look at the fractional distillation of crude oil. Now I put here a diagram which is your fractional distillation that you would do in your lab. And I put it beside the actual industrial fractionating column, the tower. Okay, the principles are similar and I'll walk you through them shortly. Again, have a look at this video that will take you through the basic principles.
In this video, you will learn how fractional
Hold on, look like something is freezing. Yes, something is freezing. Give me a sec. I have a lot of things open on the computer, so give me a couple seconds, please. All right, while it fix it, while the computer fix itself shortly, let us talk about the fractional distillation. Now, think of, all right, here we go. Good, here we go. It's coming up. Think of, let me see if we play. Hold on.
In this video, you will learn how fractional distillation separates crude oil into useful fractions. Crude oil is the term used to describe unprocessed oil. That is oil that has been taken directly out of the ground, either on land or under the sea. It is an exceptionally valuable resource. It provides us with a great number of hydrocarbons, some of which are useful as fuels, and others are used in the manufacture of many different chemicals and even plastics. However, in the raw form as crude oil, it can be a viscous, dark-coloured tar-like consistency, and the different fractions of hydrocarbons must be separated by fractional distillation for them to be useful. Before we understand how fractional distillation works, we should be clear that crude oil is a mixture of hydrocarbons with different chain lengths, some being short molecules and some being very long. Intermolecular forces act between molecules, and the longer the molecule, the greater the intermolecular force. As you can see here, the small molecules have weaker intermolecular forces, and so will require less energy to break them apart and turn them into a gas. They have a lower boiling point. The longer molecules have greater intermolecular forces. More energy is required, a higher temperature will be needed to evaporate these molecules. They have a higher boiling point. Now we understand how chain length is related to the boiling point of a molecule. Let us look at how this method works. As you can see, crude oil is heated up to a high temperature outside of the fractionating column. The hot crude oil, now mostly in vapour form, is pumped into the column. The column has a heat gradient and is very hot at the bottom, going cooler as we move up to the top. Even at the very bottom of the column, where the temperature is still high, some long chain molecules with high boiling points begin to condense back into a liquid. These are collected at the bottom of the column. The rest of the molecules start to rise up the column, making their way through bubble caps in each tray. The bubble caps slow down the rate of the rising vapour, and eventually the vapours get too cool, condense, and are collected as liquids in the trays. Small molecules have low boiling points, and so condense much higher in the column, where the temperature is cooler still. As you can see, hydrocarbons with similar boiling points are collected in the same tray, and this is why they are known as fractions. They are mixtures of hydrocarbons with similar boiling points. Each fraction has some important uses. Some examples of fractions are petrol, useful as a fuel for cars; naphtha, used in the manufacture of chemicals; kerosene as aircraft fuel; diesel oil, used as fuels for vans, cars and lorries; and bitumen, a mixture of large chain hydrocarbons used to lay roads. Now, at the end of this video, you should understand that crude oil is a mixture of important hydrocarbons, and that fractional distillation is the method used to separate crude oil into useful fractions with similar boiling point. You should understand that small chain molecules are collected at the top of the column since they have lower boiling points, and larger chain molecules are collected further down the column as these have higher boiling points.
All right. Now, based on that, class, this is your fractionating tower, and this would be our column. All right. The principles, again, as I said, they are the same. So I'm going to come here for a second, talk about fractionating column, and I'll come back to the tower. Now, let us look at this section here. We have a mixture, and let us say we have 3 molecules or compounds in this mixture. We have A, which is yellow, represented by our yellow. We have B, which is blue, and C, which is red. Now, If you start to heat your mixture, you'll notice something will happen. Remember, your mixture will have above it all vapors from A, B, and C. All vapors will be above the liquid. They will all rise up the column. But remember now, this part is hotter than this part. So as you go up, it gets cooler. Now remember, ladies and gentlemen, if I say something and you don't understand, stop me immediately and I'll go over it. So this part here should contain, let me put it there, should contain some red and it should contain some blue. Okay, they're all vapor above the liquid. Now, let's say we start to heat our mixture and we reach 50 degrees Celsius, so the vapors are there. Notice no one, all the elements, A, B, and C, the molecules, no one has reached their boiling point as yet. Now, once you reach your boiling point of, say, 60, pay attention to the thermometer here. The thermometer will stay at 60 until all of A is driven off and collected. All right, so that's how we know when to move the flask. All right, so you watch the thermometer. So we're heating. Now everything is going up and we reach now the boiling point of A. Remember now, people, you're going up the tube here. So the vapor, the gases, they are touching the beads. Now let's say you reach 60 degrees Celsius. Look at yellow. Yellow reaches its boiling point. So the thermometer should stay at 60 degrees Celsius. It will not move until I remove all of A. Now, is B and C going up with A? Yes or no? Is it going up with A? Any answers so far, Doc?
Not yet. There's a no, and there's a few more no's. No, sir, no, no, no.
All right, well, I'm telling you, all the vapors are going up with A. But look at what happens. When they come up and they touch the cooler beads up here, they will now condense, because remember now, they are not yet at their boiling point. So the vapors will go up as a mixture, but only the one that reaches its boiling point will pass right through the beads and go up and then come off as a fraction. The others will come up along with it, but once they touch the cool beads, they will then condense and fall back. This condensation will release heat, and the yellow molecules will accept that heat and use it to power themselves through the column. So in other words, it gives them more energy to go through, while the red and the blue molecules will fall back into the flask. Any questions so far?
Not yet, not yet.
All right. But you understand that all vapors are going up, but once you're not yet at your boiling point, you will cool, condense. And the one that reaches its boiling point will pass through and will collect the heat from the vapor that condensed and fall back. And that energy will help it to propel it through the beads, and then it will come off as a fraction. Are we clear there?
Okay, clear. Yes, sir, understand.
Good.
Right.
Remember this now. Fractional distillation. The process is boiling. So you boil to evaporate, and then you condense, and then you reboil. So it is just a process of boiling, evaporation, condensation, reboiling, or reheating. Now, look now, class. All of A came off. What will happen to the thermometer? What will happen to my thermometer when I remove all of A, which is the yellow molecules?
Send your responses in the chat, students. Change temperature, question sign.
Yes. So the temperature will start to increase because now we remove A. Wherever, for physics persons, wherever you have a change of state, right? You have no change in temperature. We call it latent heat, okay? So this, once I remove all of A, my temperature now will now start to go up. When my temperature is going up, do I have any blue or red coming off while my temperature is increasing? Let's say I reach 65. Will anything come off?
No, no, sir.
70.
few more no's.
79.
Still some more no's.
80.
All right, I'm seeing a few yeses.
Yes. Will the temperature stay at 80 or will it move to 81 right away?
All right, somebody says stay.
It will stay at 80.
Stay,
Now,
yes.
good. Will both blue and red molecules move up in the column?
There's a no and a yes.
All right, remember we said that both will be moving up, but what will happen to the red one?
Okay, so there's a response. Yes, but the red will fall back down.
The red will condense. Once it touches the cool beads, it will condense and fall back. While the blue now that reaches its boiling point will pass through and come out through the condenser. And now you can take that off as a fraction. So the red will fall back, and then now, remember, as it falls back, it will do what? Who can tell me what happened to it as it falls back? As it falls back into the flask?
I think somebody had written condense. I'm not sure if.
Yes, but remember,
once
it condenses, it releases heat.
Okay.
And that heat, the molecules that reaches its boiling point will accept that heat and use that energy to propel itself through the beads or through the column and come off easier. Clear? So again, boiling, evaporation, condensation, reboiling until you remove all of the fractions that you want to separate. So fractional distillation is a method that we use to separate mixtures or liquids with similar boiling point. And note I did not say same, I said similar boiling points. So the boiling points are pretty much within a reasonable range of each other. And that's how you separate these liquids. And they are miscible liquids, so they mix completely. All right, are we okay so far with that? Are we okay? Doc, what are they saying? Are we okay?
There are a few yeses. Yes, sir.
Okay.
They're saying yes.
All right. Now let's look now at fractional distillation of your crude oil. Notice that as you saw from the video, the crude oil, which is the mixture of everything, comes in and it starts to boil. Now down this side, you see about 350 to 400 degrees Celsius. Along the column or the tower, you have different temperatures. So if this is about 350 to say 400, here will be below 350. So here might be maybe 340. Here might be somewhere 200. Here might be somewhere 100 and so on. So the higher you go, the cooler you will get. Now, how do you separate that? You saw that the longer the carbon chains, the stronger the bonds. Now, please look at this class. I don't want to misunderstand this concept. If I have 1, 2, let me use black, sorry. Let me use black. If I have 1, 2, 3, 4, 5, 6, and let's just pretend that we have on our hydrogen because these are hydrocarbons. And I have another one, 1, 2, 3, 4, 5, 6. Now we have a force between the molecules, okay? And that force of attraction is what will affect the boiling point, okay? So the heavier the molecule, because the chain length is longer, then the stronger the intermolecular force is. Let me know if we're okay with that concept.
Yes.
All right, so here we now have a lighter or a shorter carbon chain. So being shorter, it will be lighter. And if it is lighter, it means then that the intermolecular force is not as strong as the one that contains 6 or 7 carbon chains, carbon length. What do we say about that now, class? What do you say about that? Which one will have the lower boiling point? This one or this one? 6 or 3?
You want to name them A and B?
All right, A. All right, let's call A. Call that one A and call this one B. A or B?
Okay, so seen some B's. Yes, B, 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 B.
So B is lower. So lower boiling point. And A would be the higher boiling point. So you link boiling point to the intermolecular forces, okay? intermolecular forces. Now, class, let me give you a word, and that word is volatility. Volatility. Volatile. Volatile is linked to boiling point. So what should you know? Lower boiling point, more volatile. Okay? Higher boiling point. Put BP. Higher boiling point. Then you are what? You are less volatile. This means that the one with the lower boiling point, the bonds will be broken easier than the one with the higher boiling point. Let's talk about something that you know about. Alcohol. Who can tell me the boiling point of alcohol? And we'll talk about water as well. What's the boiling point of alcohol?
Type in the chat or indicate which one would have the lower boiling point if you don't have the exact value.
Yes, you don't know the exact value.
Okay, what's the boiling point of water? Students, type in the chat. Okay, no responses yet. Oh, thank God, there's 100.
So,
water 100 degrees.
100 degrees, yes. And
yes.
Alcohol, let's say ethanol is at 78.
Yes, somebody has 78, yes.
Yes, all right. So let's say ethanol is 78. So will these two mix together completely? Will they mix? Are they miscible?
Somebody says no. There's a yes.
All
there
right.
are a few no's.
Thank you for your answers. But no, going forward, you should know that they are miscible.
Yes.
Okay? Their forces are similar. Both contain what we call hydrogen bonds. Okay, remember, we have an O and an H in the alcohol, and we have an O and an H in water. All right, I'm not going to go through the concepts of hydrogen bonds now, but once the type of bonds are similar, they will be miscible. So water and alcohol will mix completely. Now, if I want to separate water and alcohol, what method would I use to do so?
Somebody says boil.
Yeah, but be more specific.
Fractional distillation.
Fractional distillation. Okay. So alcohol having a lower boiling point will be more volatile, meaning the bonds will be broken much easier and it will go into its vapor state quicker. That is why if you put alcohol on your skin, it feels cool because it is evaporating. And as it evaporates, it removes heat from your body and your body feel cool, okay? Water will take a longer time to evaporate. So you can test it. You can get some alcohol, put it on the floor, get some water, put it on the floor when the sun is hot up in the sky, and then observe and see which one will evaporate faster. The more volatile one will disappear faster. Water will take a while because water really, even though it evaporates, it will take a longer time if you put a lot on the floor, okay? Are we okay with that principle so far?
Yes.
All right, just making sure, class. So the longer the chain of the hydrocarbons, they will stay lower, and the lower the chain length, the higher they will come off. So that is why we have bottled gas coming off at the top. Now, class, I'm sure you've heard about methane, ethane, and propane, and some persons butane, because these are what you use in your kitchen. All right, well, mainly propane and butane as cooking gas. So these are the gases you use to cook with. Now notice here, class, small molecules, like for example, and I'll show you your methane, your ethane, and propane, they have low boiling point, which means that they are very volatile, okay? And this is why we use it as fuel. We cook with it. And if you're overseas and you live in cold areas, you use it for heating, all right? Because it ignites easily. The larger molecules, of course, those now will have what? Stronger intermolecular forces. And the stronger the intermolecular forces, the higher the boiling point, which means that you are not very volatile, all right? And you do not ignite as easy as the smaller carbon chains, okay? So as you go up, the different fractions will come off, all right? And you see the lighter ones, the smaller chains will go all the way up through the column and come off at the top here. And then now the different chain length will come off accordingly. So the shorter chain length at the top and the longer chain length at the bottom here. So what do we have? You have your bitumen, which is used for roads and roofs. You have your fuel that is used for ships and power stations. You have your diesel used in trucks and some cars and buses. You have your kerosene, which is aircraft fuel. And of course, if some grandparents hear this, that they said the kerosene is used to light lamps in their homes. All right. You have your naphtha, which is used for making chemicals, and your petrol, of course, used for fuel and cars. And of course, the gases used for fuel to cook your food, etc. All right. So let me show you another table. Hold on. Another table. This is just going through the same principle, all right, of condensation, evaporation, reboiling, going all the way up to the top there. So this is the table, class, we're looking at. To remember now the different fractions. Now, something that I use with my class is just something that I help them to remember it. It might not make any sense to you, but you can think about it. If you want to use it, then feel free. I use real, let me do it over here. Real for refinery gas, people for petrol, and of course, naphtha is below petrol. So real people, kerosene, let's use no, and for D, we're using that, okay? We're Jamaican, so we can say that. So real people know that. L, lubricating oils, we'll say love. And B, for bitumen, we say blinds. So love blinds, okay? For those persons who know about that kind of stuff. Real people know that love blinds. So your real is your refinery gas, okay? And we know we use that for cooking and so on, heating, manufacture of petrochemicals. People, petrol, fuel for cars, and so on. Your no is your kerosene. Of course, think of your fuel for your jets. And of course, I mentioned the kerosene lamp earlier. That, diesel, fuel for diesel engines. Some cars use it, trucks and so on. Love, your lubricating oils and waxes. Those places that deal with heavy equipments will use this to lubricate the moving parts. So you have lubricating oils and waxes, love, and blinds, bitumen, used for road surfacing and roofing. So real people know that love blinds. That will help you to remember the different fractions. Of course, blinds, bitumen. This one is the easiest one to remember. Road surfacing and roofing. Love, lubricating oils and waxes. Okay, that your diesel oil. No, kerosene. And you could put there the paraffin. If you see paraffin in the multiple choice, you know it is close to the kerosene. And of course, your petrol and naphtha and your refinery gas. Are we okay so far? Any questions before I move on?
Not yet.
Not yet. All right. We have a few questions to run through now, but I want to complete some theory first, and then I'll run through some questions with you.
Sure.
Now, let us look now at cracking, because our hydrocarbons are cracking. Now, I am a bit, what I do when I'm teaching this topic, I teach alkanes before I teach cracking, because cracking is a reaction of alkanes. So I think it makes more sense to do it that way. But it is there in the syllabus at this position. I'll speak a little about it, and then I'll say more when I reach alkanes. So cracking is simply breaking up of your larger hydrocarbons into smaller ones. Cracking is the way we make alkenes. So it's a way of making alkenes in the lab. You crack it, you break it up into smaller pieces. Now you can get one alkane, you can get one alkene. Most times you get one alkane and more than one alkene. It depends on the length of the carbon chain. The examiners, however, will ask you and tell you what fractions they require, so that we don't give a myriad of answers. And it is easier for them, of course, to when doing the marking, okay? So let's talk about cracking. Cracking, of course, is breaking up your large hydrocarbons into smaller ones, or more useful ones. For example, if you have 10 is not so useful, you want to maybe break it down to like 8, because 8 now we can use that in cars. For the gentlemen who know about fast cars, you know we use something called octane boost in our cars. And the octane is this C8, 8 carbons, all right? And that will help with the driving of the car, make it more, give it a higher performance and so on, all right? So you have cracking, and we have 2 types of cracking. You have your thermal cracking, you have your catalytic cracking. your thermal cracking deals with high temperatures without a catalyst. So the high temperature is about 700 to 800. If you say 850, you are correct. If you say 750, you are okay, as long as it is somewhere within that range. And when we reach now the catalytic cracking, we still need the temperature, but it is not as high as 700 to 800. We have about 450, we say is about moderate to low. So 450, and the catalyst we use is silica or alumina. At the 6th form level, we have a more efficient catalyst, which is your aluminosilicate, aka zeolite. But right now, just focus on silica or alumina as your catalyst when doing catalytic cracking. So you break up your larger hydrocarbon into more smaller units, smaller units that you can use for various things. All right, so let's have a look now at that part. Don't forget the 2 types of cracking, class. Come on, what's going on here? All right, give me a sec. Oh, come on. Give me a sec, it's freezing again.
Oh, what's happening? Okay, students, remember, if you have a question, you can raise your hand.
Yes, let's talk about
We'll allow you to ask your question.
some questions now until the computer free me up again, please. I have a lot of.
All right. If there's something that you're not understanding, you can raise your hand, ask your question.
Yes. Everybody following so far? All right, so here we have our large hydrocarbon. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Now we break it up. Now it's like balancing an equation. Once you have 15 on the reactant side, you must have 15 on the product side. So the number of hydrogen and carbon must match what's going on the left and on the right-hand side, the reactant side and the product side. So we have what is called mass balance. We know about mass balance when we balance equations, right? You must have 2 types of balancing, your mass balance and your charge balance. In this case, we're just focusing on mass balance. Now I'm going to show you when I reach alkanes, how to know what to write for your products. So if I say break up hexane into butane and ethene, you know what to do, okay? So I'm going to come back here when I finish with alkanes, and that will help with this part as well. So let's discuss some questions. Have a look at these questions, class, and let me hear if you have any answers for me. Petroleum is refined. What does that mean? And how is it carried out? How do you refine your petroleum? Any answers?
Not yet. Not yet.
Not yet, okay.
Students, you put your answers in the chat. If you want to raise your hand and answer directly.
Yes. Petroleum is refined. What does that mean? And how is it carried out?
No one is brave enough yet.
Petroleum is, so wait, you don't understand what
okay, there's one. Oh yes, we're saved. Taking out the impurities and by fractional distillation. That's a
right.
first answer.
Taking out impurities.
I guess they're answering what refine means. And by fractional distillation.
All right. Good evening. Good evening. It's Deorville, Mitchell.
Yes.
All right. So you're getting the fractional distillation part correct, which is how is it carried out? That is correct. When you refine petroleum, remember, you are separating the different fractions based on their boiling points. So the ones with similar boiling points will separate, okay? Or you could say the one with similar number of carbons. So the longer the carbon chain length, the lower you will be in the column, and the smaller carbon chain length will be higher, okay? So it is refining simply means separating your fractions based on the similarity in boiling points. All right, and it is carried out by fractional distillation. All right, let's continue. I will show you the answers there. One compound is petroleum. Well, one compound in petroleum has 15 carbon atoms. Another has 5. Which has the higher boiling point? 15 or 5? Higher boiling point. 15 or 5?
Okay, I've seen some 15s.
15.
There is a raised hand from De Orville.
Yes, go ahead.
One sec.
Good
Sorry.
Yes, good afternoon. Go ahead, sir.
sir, my opinion would be 15 hydrocarbons. No,
You,
sir, rather the one that has 15
carbon.
carbon atoms.
You want to tell us why?
Yes, sir. I've learned rather in a table, sir, that for example, bitumen or asphalt that would have more hydrocarbon.
All right.
Than,
More carbon.
yes, sir.
Yeah.
More carbon than like the refinery gases or kerosene or paraffin.
And remember now, the more carbon, then the greater or the stronger the intermolecular force. So
Yes,
the
sir.
15 carbons would have a stronger intermolecular force than 5, hence would have a higher boiling point. Are we clear?
Yes, sir. Totally.
Thank you very much. All right. What about which fraction from refining petroleum is used in road building?
All right. So there's somebody's answering bitumen.
Yeah.
Vitamins, yeah. Bitumen all the way.
Good, good. What is the link between fossil fuel and global warming? Let me see if you're thinking. What is the link between fossil fuels and global warming?
So there's somebody says combustion.
All right.
Emissions.
Combustion and what? Come on, expand.
There's emissions.
What emissions?
Combustion of fossil fuels, the gases produced from the mining, release of carbon dioxide, CO2.
Yes. So listen carefully now, class. And I'll get to combustion because that's a reaction of an alkane. It's also a reaction of alkenes. When you burn hydrocarbons, you always produce carbon dioxide and steam. Steam is a gas, but it can condense at room temperature to form liquid. So sometimes you might see in certain books, you might see G as a state, or you might see L. All right. I don't think anyone is incorrect. All right. Unless they say at room temperature, they know it must be liquid. Now, class, when you burn hydrocarbons, you produce carbon dioxide. Carbon dioxide is considered to be a greenhouse gas. What does it mean to be a greenhouse gas? The gases now will go up into the atmosphere. All right. You have first the troposphere. It will pass and go into the stratosphere. And in the stratosphere is where you have ozone. The ozone layer is what protects us from the harmful UV radiation from the sun. Okay. What happens is that when the light comes in from the sun, it warms up the earth and the heat is re-radiated back out into space. Sorry, there's a truck passing. It is re-radiated back into space. When you have a lot of greenhouse gases, what that does, it goes up into the atmosphere. Let me just give you a quick little diagram so you know what I'm talking about. Quick diagram here, class. 1 second. Let me draw the earth. Earth. Where's my earth? Come. Earth. Let's draw the sun. Sun with rays. And let's show you the radiation coming down. Yellow radiation is high energy radiation. Let us draw ozone. Let's draw the ozone. Let's set the sky blue. Let's draw ozone for the sky there. So, and then now you have it coming in. The earth absorb it. That's the earth. Let's draw. Let me see if I can draw Jamaica. Something like that. Jamaica look like. All right. It comes in, and then now it is re-radiated as longer wavelength. So it passes through the ozone and goes back out. Of course, some will bounce back onto Earth to kind of keep us warm. Okay. However, when you have the greenhouse gas now, carbon dioxide does this. It surrounds the ozone layer. All right. This is carbon dioxide trapping the heat now, and the heat comes in, and now it cannot go out. Cannot leave. And then we have now global warming, which is simply the warming of the globe, and the temperature of the earth goes up. And then you can link that now to more dangerous hurricanes, drought in some areas, and all that good stuff. Not really good stuff, but you know what I mean. Any questions so far with global warming?
No question. Somebody saying they're not seen. Probably the marker is probably a bit pale, the color.
Oh yeah, I use yellow for my sun and red for my infrared and so on. That's why. And the green is for my carbon dioxide. All right, but we can discuss this another time. So anytime you burn hydrocarbons, it is good because you need the energy, but you have to bear in mind that you can cause global warming. So the more CO2 you release in the atmosphere, the greater the global warming and the hotter the time will be. All right, let's continue. Let me clear the screen and move right along. Let me see if I can find another the answers first, and then I'll go to another question. So here we go for the answers class. Separated, first one. How do you refine? Separated into groups of compounds with similar boiling points, and the process is fractional distillation. The one with 15, you know why. Bitumen, you know why. And of course, carbon dioxide is our greenhouse gas, which contributes to global warming. How are we so far? We're good?
Good.
One question now, class, for you to look at so you can see what is going on. Let me find it here. This question here is, where is it? You can take a picture of this question here, class, this one. Crude oil consists of a complex mixture of hydrocarbons. This is a long time paper, 2001. Mixture of hydrocarbons, most of which are alkanes. The fractional distillation of crude oil results in the separation of fractions with different properties and uses. State the steps involved in fractional distillation of crude oil. And then now the chemical principles upon which the separation process is based. And of course, list 3 fractions that are obtained from crude oil, which you can, based on what I told you earlier, and then state the use of each fraction. So you could talk about bitumen, refinery gas, kerosene, lubricating oils and waxes, any one of those. Let me know if you have the photo of this question so I can move on. So the only thing left to do in sources is to go back to looking at the fractions, because you'll see we have questions on that in this particular document. So we're good so far with hydrocarbons, sources of hydrocarbons?
Yes, there's a yes.
All right, so we can make sure you can identify both natural gas and petroleum, and you can list the main sources or uses. Well, source and then use, and the principle is fractional distillation. And we understand the 2 types of cracking, thermal and catalytic. Just to go back now and fix up now the fraction. Well, when you break up your large hydrocarbons into your alkane and alkenes, which I'll do when I finish alkanes. So I'm going to go into now part 2 of section B, which is organic chemistry, the introduction. So we'll go and look at why carbon can form so many bonds with itself. All right, let's go there. All right. We're going to keep it as simple as possible because it is more complicated than just saying that carbon is tetravalent. But at this level, we're going to leave it at that. So carbon, who can tell me the mass number of carbon and the atomic number? Mass number and atomic number of carbon. What's the mass number?
Okay, I'm seeing 12 atomic number. 12.
No, I want mass number first. Mass number.
Okay, I'm seeing some 12s that didn't have any
12 is the mass number. What's the atomic number?
Yes. 12 and 6, 6 and 12, 6, right. 6 are atomic.
Good. What is the configuration for carbon? The electronic configuration?
2, 4, 2, 4, 2, 4.
4. Now listen to me very carefully. We are studying organic chemistry, but let me just say to you, when it comes on to inorganic chemistry, all right, valence electrons is responsible for reactivity. So valence electrons, this is responsible for reactivity. When we deal with organic chemistry, we are not concerned about valence electrons in terms of reactivity. We look at what we call functional groups. So when things react in organic chemistry is because or due to the functional groups. For inorganic chemistry, reactivity is due to valence electrons. Let me know if you are clear on that.
Yes, clear.
All right. So all I'm doing now is showing you the reason why carbon is able to bond to itself. All right, because it is tetravalent. So I have 4 valence electrons. So another carbon can come and bond with it. Let's use red in this case. So that's 1, 2, 3, 4. And the same thing will happen right around. So carbon is able to bond to itself. For those of you who know about diamond and graphite, you know that it looks something like so. Let me just do a quick sketch. Looks something like this. And you can continue with the structure and so on. Is that so?
Yes.
All right, so this is your carbon, your diamond. Now, the reason why diamond will not conduct electricity is because all 4 electrons are used up in bonding. Tell me if you're okay with that. Oops. Yes?
Yes, there's a.
Will graphite conduct?
So there was a no and there's some yeses.
For graphite?
Yes.
Graphite will conduct. Now look at this class. In diamond, all 4 electrons are used up in bonding. Now, if you look at the shape of graphite, you'll see that I have 1 carbon here, but it's only bonded to 3 other carbons. 1, 2, 3. So if that's the case, in graphite, this is what you have. 1, 2, 3. I have 1 valence electrons here, free to move. And remember, electric current is the flow of charge particles. And electrons, that's a charged particle, and then you have ions that you deal with in electrolytes or electrolytic conduction. So graphite will conduct current, not diamond. Are we okay with that so far?
Yes.
All right. So since I'm here, I'm just making sure to remind you of a few things. All right. So carbon having 4 valence electrons can bond to itself. We call that at the 6th form level, we call it catenation. It's the ability of an element to bond to itself. All you need to know is that carbon can form chains and rings and branch compounds because it is tetravalent, which means that it is able to bond to itself. So this is the most important part right here. See, where is it? Carbon is tetravalent, therefore can bond with 4 other atoms. Okay, so anybody asks you, why is carbon able to bond to itself and form chains, branch, and rings? You say it is tetravalent and it has the ability to bond to itself. Okay, I have a question here. What is organic chemistry? Organic chemistry is the study of carbon compounds, except carbonates, carbon monoxide, and carbon dioxide. So those would not be considered as organic chemistry. Those would be considered as inorganic chemistry. Okay? So we now know why carbon can bond to itself. So let's move on. This now is the homologous series. Now listen to me very carefully. Go ahead and take a picture of this because I have several questions to ask as I move through this topic. So take a picture of the homologous series while I discuss it. All right, D'Arville. What was your last name, D'Arville? Was it Morgan?
Mitchell.
Yes.
Mitchell. All right, D'Arville. Your last name is Mitchell. Do you have brothers? Yes or no? I didn't hear you.
I'm afraid not. I only have 2.
You're afraid no? Oh, that's all right. That's all right. All right, let me use myself then. I have several brothers. 7 brothers. I'm the 8th. So if you belong to a particular homologous series, okay, it means that you belong to a certain family of compounds, okay? So your homologous series, think of the family to which the compound belong, all right? All my brothers, we are, if you see any of my brothers, you see me. Why? We resemble. We behave the same way. Sometimes we talk the same way, all right? I don't know if you notice, I have a little lisp, I have a little stutter, and so I talk a little fast, you know? My other brothers have the same trait. Why? We belong to the Burrell clan. Am I making sense?
Do they love basketball too?
Well, they love sports. They love sports overall. Yes, so I would say yes. Okay? So we share a lot of things because we belong to the same family. Same thing with organic chemistry. Members that belong to the same family belong to the same homologous series. We're looking at alkanes, we're looking at alkenes, alcohols, and carboxylic acids. Did I say alcohol? Yeah, I said alcohols. All right. So all the members are represented by the same general molecular formula. Soon discuss that. If you belong to the same family, you have the same last name. Let's say you know about the same last name. We're not talking about those might have a different last name. But if you have the same last name, right? Every alcohol, let me say methanol, ethanol, propanol, they have similar chemical properties or characteristics or reactions. Who can tell me why? What is the reason why they have the same chemical properties? What did I say earlier? If you're an alkane or alcohol.
Functional group, same family.
Thank you very much. The same functional group. Remember I said it in a class. Once you belong to the same functional group in organic chemistry is what is responsible for chemical properties, chemical reactions. When it's inorganic chemistry, it is valence electrons. So if I'm reacting sodium with chlorine, well, the valence electron must be lost from one and the valence shell will accept the electrons. That's reactivity. Okay? When it's organic chemistry, it's not valence electrons. It is the functional groups that will determine the type of reactions. So remember the second one. There is a gradual change in the physical properties. No, list this for me, please. Change in the physical or gradual change in the physical properties. Let me write the word physical properties. I hope you can see my handwriting. Properties. I'm sorry if I write so ugly. I'm trying. Physical properties. All right, now we spoke about melting point / boiling point. These are physical properties. What else? What else, class? What other physical properties you can think of? No? All right, what about solubility?
Okay, so I'm seeing density.
Density.
Somebody says intermolecular force.
All right, that's a property that will be linked to the melting point and boiling point.
That's
so
the explanation.
Yes, we use intermolecular force to explain the MPBP. So good attempt. All right, density is fine. You could say density, that's fine. Let me use rho for density for physics. Rho, density. All right, let's focus on these two for now, however. Look at this class. 2 carbon chains, and now I have 1, 2, 3, 4, 5, 6. Let's call this one A, let's call this one B. Which one would have the higher boiling point? Let me just say / melting point. Which one would have the higher boiling point? A or B?
Okay, some B's. B.
Good. Which one would be more soluble in an organic solvent? More soluble in an organic solvent.
Seeing a few A's.
A. Good. You see why? The lower the carbon chain, the more soluble. The higher the carbon chain, the less soluble. Is that making sense? And of course, the more carbon chain you have, the more dense you'll be. So we're good so far with these properties?
Somebody's asking, why is that so?
Which one? Which one?
I'm supposing it's the one about the soluble in the organic.
All right. Thank you for that question. Let me go back to my board and show you. Organic solutes. Organic solutes are soluble in organic solvents. Why? Organic solutes are non-polar. I hope you understand this term, non-polar. You don't have a different charge from one end to the other. So if you're non-polar and your organic solvent is also non-polar, then it will dissolve organic solutes. Tell me if you're okay with that before I continue.
Okay, there's yes, they're saying yes.
Good. Now, if I dissolve a non-polar solute in water, should it dissolve? If you're non-polar solute and I put you in water, should you dissolve?
No.
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 Water
Okay.
is what? Water is what?
Okay, so it's what? Yeah, polar. They're given polar.
Water is polar. So even though we know that water is a universal solvent, think of it in this case, in the sense of if you are non-polar, you will not dissolve in water because water is polar. Water will dissolve only ionic solids or polar solids. Are we clear? Yes, we're good?
Yes.
Good. Now, the reason why the one with the larger chain, carbon chain, will be dissolved less in your organic solvents is because you have more carbon atoms are to break. The carbon chain length, the more you have to break, the less soluble. The less you have, right, the more soluble. Remember the intermolecular forces between the larger one and the smaller ones? So solubility would be the smaller the chain, the carbon chain, the easier it is to dissolve. The longer the carbon chain, the harder it is to dissolve in your organic solvent. Tell me if you're clear with that part so far.
I think Brittany Manning wants to ask a question. Brittany, could you raise your hand so I can unmute you?
I hope I answered the other lady's question, the other student question.
Yeah. Okay. Yes. Give me a Brittany. Oh dear.
I was asking then for the melting point of the long chain one, why is it easier to melt?
All right, remember now, that's why I said earlier, all right, whenever you do physical properties and they ask for it and you're giving them melting point and boiling point, they don't normally like to separate them. So I just normally put melting point / boiling point. Clear? Melting point would be mainly for solids. Clear? Boiling point mainly for liquids and to some extent gases. So I just put melting point, boiling point because it's normally you put them together. You don't separate them. You follow? So if you have a solid and the intermolecular forces are stronger in that solid, in order for it to melt, don't you need more force to break it down? Are you there?
There, I'm here.
Yes. Yeah. Are you understanding what I said about the MPBP being placed together?
Yeah, I got that.
Yes. So I just put melting point / boiling point because you normally put them together. However, when you explain like things with liquids and so on, you don't really use melting point. If you get my drift. All right. And we are working with only gases and liquids up to the first, 10? Yes. So depending on which one you're looking at, the first 5 or the first 4 for alkanes and alkenes are gases and the rest are liquids. All right. So don't focus too much on the melting points just yet. Are you okay?
Okay.
All right. So we're okay with the general molecular formula. We'll soon come to that. Members display similar chemical properties and the gradual change in the physical properties such as carbon chain increases. So in terms of looking at the solubility and the boiling point, let's leave that boiling point. And then now the relative molecular mass increases by 14 or CH2. Okay? Or you could say the carbon chain increases by 1. So let me show you that one, class. You tell me the difference between these two compounds. So let's go 1, 2, 3, 4. And I'm going to go 1, 2, 3. Put on my H's. What is the difference between this molecule and the one below? What's the difference? Anyone?
There's somebody saying the amount of carbons, number of carbon atoms, length of chain. One has 3 carbon, other has 4. One is longer. Hydrogen differ by 2.
Yes. So the CH2 is a difference. You see that? So if I remove CH2 from the one with 4, I end up with CH with the one.
I think you have a hydrogen missing from the first one.
Yes. Yes. Let me put it in. Yes, I do.
Yes.
There you go. So look at that now, class. You see it? So the difference is CH2, which is 14. Carbon is 12. H is 1, but we have 2 of them. How we say?
No response yet.
All right, but come on, ladies and gentlemen. Let me know if you're all right, man.
Good, so somebody didn't get that, so you could probably go
all right, look again. Suppose I have methane. Let's go with 1 carbon here. And if I want 2 carbons and I want it to be an alkane, what do I need to add? What do I need to add?
Brittany says CH2.
All right, so let me add the CH2 right here. Look, I'm gonna add CH2 right there. So now I have H. Let me keep this H here, and let me change this now and put CH. You see the CH we add to this to get this?
Yes.
So the difference between this and this is CH2. And the difference between this and this is CH2. Is that clear?
Yes.
All right. Thank you. Let's go back to this. So you need to know this because we have questions where they're asking you to list. Let me find one for you. Let me just find one question for you that asks you to list it. All right. Where's my, let's come here. Let's check this one. See it here? What is it, people? List 3 characteristics of a homologous series. How many did I give you a while ago? Did you take a picture? How many?
Said 4.
4. You can list 3 out of the 4? So that? So it's important to know them. Okay? Are we okay?
Yes, they're listing some of the properties.
Yes. Good, good. Right. So just 3 out of the 4. All right. Good. Let's move on now, class. Look at this now. Now, remember this part? Members can be represented by the same molecular formula. Look now, class. And you must know these because I know some persons are going to make mistakes with this one. So let me say this to you, class. Let's discuss the general molecular formula for the various homologous series. Let me go to a blank page and start with alkanes. All right, pay attention now. Alkanes first. Alkanes. Now for alkanes, the general molecular formula is CnH2n plus 2. N representing number of carbons. Tell me if you're okay with that.
Yes.
All right. So let's record this one with 1, 2, and then 3. So it's C1, H what? C1, H what?
Oh, sorry, I was muted. 2, 2, 4, 4.
All right, so 2 1s, 2 plus 2, 4. So normally we ignore the 1, so we just simply write CH4. This is the simplest alkane. I will call this one methane. I will soon discuss the name. Methane, simplest one. Are we okay with that so far? Someone mic open. Talk to me. Come, n equal 2.
They're saying yes. Okay, I'm not.
Give me n equal 2 and then n equal 3. N equal 2. What's the formula for that? C.
C2H6.
2H6. 2 is 4 plus 2 is 6. Give me 3.
C3H8.
H8. Look now, go into alkenes. CnH2n. Notice for alkenes, you always have 2 less H's. So give me C. Based on this, can we have any C1? Is C1 possible for alkenes?
Seeing some no's, can somebody explain?
Mm-hmm.
Who'll be brave enough to explain?
Yes, let me hear you quickly.
You can't have a one because alkene double bond with a carbon.
Thank you very much, sir. Thank you very much. Now, for alkanes, they're all single bonds. And remember, I'm going to do this when I reach reactions of alkenes, but some of the things overlap. So alkenes, you need what is called a double bond. The functional group for alkenes is a double bond, carbon-carbon double bond. The single bond, it's not really a functional group, but we use it to identify alkanes. Am I clear there? The single bond is not really a functional group, but we use it to identify. So you can say it is, but it's not really a functional group. Clear?
Yes.
So, single bonds. I just want to make that clear. So because you have a double bond, you can't have one. So the simplest alkene is ethene. So go ahead and give me C2. C2H what?
Sorry, H4, C2H4.
H4. Give me C4.
H8.
H8. Now, if I give you some formula or formulae and say to you, which group will this belong to? Or does this belong to? You look at the general molecular formula. Let me do alcohol and alkanoic acids, and then we can look at some questions there. Class, alcohols now. Alcohols. CnH2n plus 1 OH.
Okay, so before you go any further, there are a few persons saying they're not getting it. So I don't know if you want to. I think it's the.
Which part?
Well, Sharon, do you want to explain what you're not getting? And Tony Ann, can you raise your hand? Sharon and Tony Ann, raise your hand.
The alkane or the alkene? Which part?
I'm not sure. I'm going to let them speak. Tony Ann, go ahead.
I don't understand the order.
The order? Which order? I don't understand.
You have C2H4 and then you have C2H8. I'm not quite understanding.
All right. So look here. Let's do again. The general formula. We use this to identify any alkane. Okay. So this is the formula we use. CnH2n plus 2. So let me show you this, class. The carbon chains will come with a certain number of carbons. So if you're 1 carbon, 2, 3, 4, 5, 6, 7, you should be able to give me the molecular formula from the general formula. So what did I say N was equal to? Stay on the mic and tell me, class. Sharon. What was N? What did I say N was?
Number.
Number of what?
Number of carbon.
Carbon. All right. So if I say N is equal to 1, give me the formula that you'll write for when N equal 1. C what?
Cn.
C, N is equal to 1. So now focus on 1. C, 1.
1.
H.
H2n.
2 times 1.
Oh, 4. Okay.
Yeah, plot
Oh,
2.
okay. I just understand. Okay.
That's fine. So that's why you get now C. We don't put the 1, you can leave it off, and then H4. You see it? Let's do 1 with 2. Sharon, don't go. Let's do 1 with 2. No, let me switch it up. Give me 1 with 5. 2n plus 2. Give me 1 with 5 now. So C, 5. Sharon, you gone?
No,
Sharon,
I'm here.
okay. Yes, work out that one.
C5, what? H what?
Um, hold on. I'm just checking.
That's fine. That's fine. Take your time. N equal 5. What do I do?
Sharon, are you still
Hold on.
there? Substitute the 5 for N.
Where's the N? Put 5. She gone?
I think she's still there. I hope she's not drawing for a calculator.
Anyone want to help her?
Yes, there are some responses in the chat.
So 2
No,
times.
normally, when I'm doing it, if I have 5 carbon, I know that I'm supposed to have 10 hydrogen, right?
No, wait, no, but it's not as, it's not, I don't want you to say normally if you have 5, because I could, let's say if I give you C15, what should you have here, sir? You see, you can't get any number here, you know. But if you know the formula, the general molecular formula, you say, okay, then 2 times 15 plus 2, you see it? Which is 32. So C15, H32.
So you're supposed to write back the 2 times the 15.
Work it out. So you know this. You have to know this. You have to know this for the alkanes. You see it?
Oh, that's what I don't know.
Yeah, you have to know this first. Clear?
Okay, thanks.
So no problem. For alkanes, it's CnH2n plus 2. All right, so everybody okay with alkanes? Can I go to alkenes again? CnH2n. So give me C6. Anybody? C6. H what?
H12.
Thank you. One more. Let's do C15. H what?
H30.
Thank you very much. Let's go to alcohols now. Alcohols. CnH2n plus 1 OH. Let's go with the simplest one we know, the one that people drink. Alcohol, ethanol. You ready? 2. So N equal 2. So C what?
C2H5OH. There's
H5.
3.
OH.
Somebody has 3 and 5. C2H5OH.
Yes, but look here. Suppose this is C2H6O, because this is really the molecular formula. You see it? You should know that this is an alcohol as well. And you can work it out and to see that the alcohol is really, this is really this. Okay, class, is that clear?
You can do that again, just in case.
I just simply say C2, H, that was add all the H's. 5 and 1, 6, see? And 1 O left there. So this is really the molecular formula. Came from the general molecular formula, This one. That's all. Give me C4. C4H1.
Nine.
Then?
And somebody says C4H10O. I guess you're using your thing. Right, C4H9OH.
Yes, or C4H10O. Thank you very much.
Somebody's asking what is condensed formula then? And another person wants to screenshot.
Yeah, man, go ahead and screenshot. What is screenshotting? We soon come to the molecular formula and the general formula, the displayed and the structural displayed and structural condensed. Take it one step at a time. Which part you want to screenshot?
They said table. I'm not sure. Do you have a table somewhere?
Yeah, well, soon go back to the table.
Okay.
All right, one more thing. Alkanoic acids now. So let's say carboxylic acid. Carboxylic. I want L in carboxylic. I'm gonna fix this. I think, yes. Acid. Hey, who changed my screen? What's going on? Somebody changed my screen?
Really?
Look, well, I was on the whiteboard and it went back to the screen. All right.
Oh, sorry. All right.
That's fine. Look at this one. Now, class, this is where the trick is now. Look at this. CN H2N plus 1 COOH. Pay attention. How many C's do you see so far in this general formula? How many carbons? 2. All right. So look at this now. All right. 1 is meth. We soon come to the names, but let me just show you something. 2 is eth. 3 is prop. 4 is bute. So if I want one with, if I want a formula for one with only 1 carbon, what should you put there? Any ideas what to do?
No responses yet.
All right, let me say it because
yes. Well, one person says HCOOH, but he didn't give the
all right.
method.
All right, pay attention now. You see this? We have to what do we know? Account for the carbon in the functional group. You must account for it. So if I say 1 carbon, then this must become 0. So this N is always 1 less. This one. Is that clear? For the carboxylic acid. So you still give the formula as CnH2n plus 1, COOH, but bear in mind that this C is a part of the name. Are you with me?
Somebody says not clear. Go again.
All right, look here. Let's say I want ethanoic acid. Ethanoic acid. How many carbons in ethanoic acid?
2.
2. Suppose you start with Cn as C2. I'm going to put C2. C2, right? Because it's 2. I want this one. C2. H2 times 2 is 4 plus 1, 5. COOH. Is this ethanoic acid?
No, sir.
What is this?
Propane.
No, it's propanoic acid. 3. Yeah.
Sorry, propane.
So I'm saying to you, when you're doing the acids, bear in mind that the carbon in the functional group is a part of the name. So you have to take that into consideration when writing the formula for it. So if I want a carbon with 2, this N must be 1 less than the number I want because I account for 1 already in the functional group. Is that making sense?
Sir?
Yes.
So that means, like if you want to say ethanoic acid, we'll just say CH instead of the C2.
C1. If you want methanoic acid, let's go. Let me show you. I'm not hearing you. Second, please.
Sir, go ahead.
All right, watch this again. All right, let's start with 1. We want 1, right? So if I want 1, this N in the acid we're saying must always be 1 less than the number we want. Why? Because a carbon is already in our functional group. Do you see that? So if I want methanoic acid, then I can't say C1. I have to say C, N minus 1, 0. H, 2 times 0 plus 1, COOH, because this will now give me the 1. This 0 is 0, so this is gone, right? 2 times 0 is 0. So I only have 1 H plus 1. So now I have HCOOH. Tell me if you're okay with that.
Yes, sir.
So just bear in mind, for the acids, whatever they ask you for, the N should really be N minus 1. Raise hand. Somebody raise their hands there. Miss Doctor?
Yes, sir. Coming.
While we get to those persons with raised hand, let's give me one with 4 now. I want 4. What do I do? What do I say? See what? For the acid.
3.
Thank you very much. C3H, 236 plus 1, 7 COOH. Now I account for my 3 carbons here plus the 1 here, which give me 4. How we stay?
Oh dear.
We making sense?
Yes. Cummins wants to ask something. Yes, the other person said got it.
Yes.
Cummins, go ahead.
Yes, sir. So you have to include COOH in the formula.
You have to account for the carbon in the functional group. Yes.
So you remove. You couldn't have put carbon there.
Carbon
like
where?
That you remove the C right there. It could not have stayed and have something else.
No, because the functional group is attached to some other stuff that you can't separate. That's the functional group for it.
So
this
being the
functional group.
Yes.
It's separate. It's different from these, but it's a part of the name.
Okay.
So this is.
So sir, there are still. I think there are still a few more persons who are not clear. So, if you can find another creative way to explain it again.
Look here. Remember, let's look at alcohol. CnH2n plus 1 OH. Do I have any carbons over here? Yes or no?
No.
So I don't have any carbon to account for. So if I want 2, I just say C2 and continue. If I have an acid, all right, CnH2n plus 1 COOH. Remember, it's a number of carbon in the compounds that account for the name. You follow? But I have a carbon here already that you must take into consideration. So if I want 2, I can't say C2 because I'm going to form something with 3 carbons in it. You see it? You see it, class?
There's a yes.
So really and truly, the formula should really be this. The formula should be this: Cn minus 1 for the carboxylic acid. It should be Cn minus 1. H2n minus 1. Anyway, say n, put minus 1, n minus 1, plus 1, COOH. So focus on this, and you can't go wrong. But if they ask for the general formula, just give them CnH2n plus 1 COOH. But bear in mind, for the carboxylic acid, it is really Cn minus 1, 2n minus 1. You can't go wrong. So now if I say, give me the compound for n equal 3 for an acid, what do you say? Give me that one. See what? Used in this. See what?
2.
Which is 3 minus 1, not true? H, 2 times 3 minus 1. You see it? Plus 1, COOH. I say I want 3. So when I finish, I should have 3 in my name, not true? So this becomes C2H. 3 minus 1 is 2 times 2. 4 plus 1, 5. COOH. How many carbons do I have in my acid now?
Just a sec. Sir, can you unmute yourself? I was hearing some other sounds.
Wait, I was muted? Somebody mute me.
No, man, I muted everybody because I heard something.
Okay.
Probably you could, instead of say n equal 3, tell them if you want to have a compound that has 3 carbons, then.
Yes, it must have 3. But because what they have in the books, doc, is this general formula. But I'm saying to them, if they follow that general formula, they are going to end up with 1 more carbon than what they want.
Right.
For the carboxylic acid. So if it says Cn and I say I want 4 carbons, and you say Cn, you're going to end up with 5 carbons because you are not taking into account the carbon in the functional group.
Right.
So I'm saying follow this method, but if they ask for the general formula, give them this one.
Okay.
Just for the acid, because you have to take into account this carbon. That's
Right.
a part of the name. That's all I'm saying. Are we okay?
Yes, they're saying okay.
All right. So based on that now, watch this now, class. Based on that, let me come here. Based on that, look at this question here. What is the general molecular formula of the following compounds? Alkanes, alkenes, alcohols, carboxylic acid. These are questions from CXC, by the way. I just remove several snippets and put them together. So these are from CXC. So alkenes would be what?
Alkane, somebody's giving CnH2n plus 1.
Alkenes.
CnH2n alkene.
Alcohols.
Nothing yet. All right, somebody says CnH2n plus 1. I don't think it's complete. CnH2n plus 2 OH.
CnH2n plus 1 OH.
Yes, CnH2n plus 1 OH.
And now I said now for the carboxylic acid, give them the normal one that you have in the books. But we know now what to do if they ask for something from it. Are we clear? So you give back your CnH2n plus 1 COOH. But we know that if we are writing a formula for something with a certain number of carbons, we must take into account the carbon in the functional group. That's all I'm saying.
Right.
Good? Okay. Quickly, let me see if I can put these in groups. So try to make 4 groups with 3 members in each group. And then explain the basis of your grouping. I'll give you a couple of seconds. Give me a minute.
Okay, so go ahead and group those compounds. If someone wants to answer directly, you can raise your hand. Responses in the chat. And when you're grouping, could you indicate what group or series they belong to?
So which one should I start with?
So there's a one answer. Somebody has put together C2H4, C2H6, and C3H8.
All right, let me put those in. Come on. All right, what group is that? Give me the group name so I can put it there. Use the molecular formula, the general molecular formula to give me a name. Is it alkanes? All right.
Yes, yeah.
AAN, alkanes. Give me the first one again. See what?
C2H4 was given.
All right. Think of the general formula. That would not match alkane.
No, I think they were doing alkenes.
Oh, alkenes. All right, let me change this to alkenes. All right, give me again.
They had C2H4.
H4.
And C3H6.
C3.
I don't see. Is that there? It's not there.
C5H10. C5H10. What else?
All
right.
C8H16.
Thank you. So these are all alkenes. So everybody here should match CnH2n. Tell me if you're okay with that. Yes?
Yes, there's some other, yes, some
Give me
other
the
persons,
alkenes now.
some
Give me-
other groupings.
Let's go to alkenes. Let me spell it wrong too. Hold on.
Okay, so for the alkanes now, we're given C2H6, C6H14, C3H8.
C2H6, C6H14, C3H8. And they all follow CnH2n plus 2. This is N. Good?
Right. And there's,
Give me alcohols next.
all right, so somebody else had given acid. Well,
All right. You want to give me acid first or alcohol? Which one?
sorry, I think it's alcohol they gave. C3H7OH, C2H5OH.
7OH, C4H9H, and C2H5OH. And they all follow the formula CnH2n plus 1 OH. And the acids now?
All right, so the person gave CH3COOH.
Alkanoic acid. And those now are the ones with the COOH. So C6H13COOH, C2H5COOH, and CH3COOH. So we have our groups. And you notice that we have to use they must follow the general molecular formula. Everybody okay with that? What's the basis for your grouping? What would you say for this answer? The basis for your grouping?
Who wants to explain the basis? Or somebody said the formula, general formula.
Mm-hmm. But remember, they belong to the same homologous series.
Yes, somebody says functionality group.
They all have the same functional groups.
Functional.
Okay. Yes. Everybody okay with that so far? Any issues?
Clear?
All right. So I'm going to go back to the presentation then. This is what you asked for earlier. This is it. But remember, bear in mind this one. Okay? Think n minus 1 wherever you see n. For this one. This n. How we see so far? We're all right? Anybody struggling with what we're doing so far?
Okay, but says no.
All right. So we can move on.
Brittany Gray, your yes means you're struggling, or yes, you're all right?
Yes, which one?
Yes, I don't understand.
Okay, could you explain to sir?
What do you say? Yes, you understand, or no, you don't understand? I didn't hear.
No, I don't understand.
You came on late?
No.
Which one?
The question that you were doing about putting them in for, I think it's
Let me go back there for you. Give me a second. Let me find it back first. This one there. Go ahead.
yes. So it's saying that to try and make 4 groups with 3 members. I don't get that.
All right. So we have 4 groups with 3 members. So we should have one with alkenes, one with alkanes, one with alcohols, and one with carboxylic acid. Can't spell. What's that mean? Carboxylic acid. How many groups is?
4.
And we should have 3 names, 3 of them in each. So 1, 2, 3. So which ones can you find that is considered an alkene? And why would you choose that one as an alkene?
Is it C2H4 for alkene?
Yes. C2H4 will be the alkene. Why? Why did you choose that? Remember the general formula?
Because it's C2H2N.
Yes, CnH2n. And because if we have 2, then the n is 2, and then 2 times 2 make it 4. So yes, so you look for everybody that follows this formula, you put on the alkenes.
Oh.
CnH2n plus 2, you put on the alkanes. Anyone that follow the alcohol general formula, go on the alcohols and so on.
Okay, I understand now.
All right, take a picture so you have it to do afterwards.
Okay, thanks.
All right, no problem. You're welcome. Let's go back to the presentation. It's hiding. Where is it? Oh, we were here. All right. Moving on now. So we have different types of formulae to consider. You have the molecular formula, you have the empirical formula, you have structural condensed formula, and you have structural displayed formula. Should I put the displayed here? Structural displayed formula. So the condensed formula, you see that the groups are closer together. You don't really see the bonds for hydrogen. All right, so you don't see here, you're seeing the CH bond here. So this one is displayed, while you're not seeing the bond here for the CH here. So this one is condensed. Are we clear so far? Yes? No?
Can you repeat again?
No problem. All right, so I'm gonna show you molecular formula shortly and show you the empirical formula is the simplest whole number ratio. So if you notice, find a number that is divisible, that can be divided into these two numbers here. And you can see 2 into 4, right? You see it? Goes 2 times, and 2 into 10, 5 times. You see it? Simplest whole number ratio. The molecular formula is the actual number of atoms present. And the empirical formula is the simplest whole number ratio of the atoms in the molecule. You okay with this?
Yes, sir.
All right. Now I'm going to the structural condensed and the structural displayed. All right. Don't pay me no mind yet. I'm coming back to this. Don't worry about that. We know this already, so we can go away from that. Soon come back to this one, to the naming. All right, coming back here. Let's look at naming alkanes, and I'll come back to some things up there. Alkanes now. Notice it's raining, so it's very loud where I am. All right, let me bring my mic closer to me. Can you hear me clearly?
Yes, sir.
All right, a lot of rain outside. All right, alkanes. What do you need to know? A few things. The number of carbons present in it, the prefix and the suffix, and then the name. So if you have 1 carbon, you're meth. 2, you're eth. 3, you're prop. Then bute, pent, and so on. I think your syllabus require up to, I think, about 5 or 6. So, but know the rest still. So it's meth 1, eth, and so on. So if I want methane is 1 carbon, so you say M. Oh, hold on, let me go back up here. I'm writing. All right, let me come to a whiteboard. Hold on. Where the thing gone again? Oh. Is somebody moving something? I'm not seeing my stuff here.
We're seeing the whiteboard. I don't think it's moving.
Just come back. All right. So it's a no. Meth is 1 carbon, right? 1. Eth, 2. 3, prop. 4, bute. So prefix is a meth, eth, prop, bute, and so on. The suffix is ane for everybody. So the name would be methane. So if you're 1 carbon, you are methane. If you're 2 carbons, you are ethane. Give me 3.
Propane.
Give me 4.
Butane.
Give me 5.
Pentane.
Give me 6.
Hexane.
6. Hexane. Give me 7.
Heptane.
All right. 8 is octane. 9 is
octane, nonane, and 10 is
right.
dectane.
Look now. I said 2 things a while ago. I said structurally condensed and structurally displayed, didn't I? Structurally condensed. All right. So let's go with N equal 1. So we want methane. So for the general formula, if I want methane, it is CnH2n plus 2. So it is really CH4. So this is the molecular formula. Clear? Clear?
Yes, sir.
From the molecular formula, I can now write the structural condensed formula, which is still CH4. SCF, structural condensed formula, CH4. Are we good so far? Yes, all right. And then now the structural displayed formula. This, something is going on right here. Hold on. Displayed formula. Now for the structural displayed, I'm going to show the bonds for hydrogen. So H, 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 H. How are we? Are we okay?
Yes, sir.
Good. Go ahead now and give me N equal 2. What is my molecular formula for N equal 2? Using this same thing. Yes, all right. So C2H6. Thank you very much. So C2H6 is the molecular formula. What is the structural condensed formula? It's going to be different now because I have more carbons. So this now would be CH3CH3. And then the structural displayed formula now is CCHHH all around. Talk to me, ladies and gentlemen. How are we?
All right, somebody said they're lost, so could you?
So do you have to write the CH3 2 times?
Yeah, yes. Because this is, remember, the molecular formula just simply tell you that you have 2 carbons present and 6 H's. Now, when you're showing the formula, you have to show how the carbons bond to each other. You see that?
Yes.
All right.
Sir, could probably, if you use a colored marker and circle the CH3 groups on the displayed formula.
Yeah, man, I come to that. Let me do methane here first. So this is methane. You see that? Are you seeing any bonds around this? Are you seeing my screen?
Yes, seeing the screen, sir. I think
so
they're absorbing.
All right. So is this displayed or condensed formula? Would you say? Tony and Cummins, hand is up, miss. It's up, Doc.
Yes, I'm trying to unmute her.
So tell me now, class, is this displayed or condensed? CH4.
Condensed.
Condensed. All right, thank you. Look at this now and tell me, is this displayed? Oh no, I did the wrong thing. Is this displayed or condensed? Let me change this. So this was the first one. This is the second one. Is this displayed or condensed? Is it displayed or condensed? No, sir, my screen is not frozen. That's your screen. Everything is fine right here. Whenever my screen stops moving, I'll tell you that my screen is not moving, but it's fine.
Yes, screen is okay.
Somebody said they're not seeing. You're not seeing what I'm sharing?
Not seeing what you're pointing on, sir.
I just did CH4 and I did CH4 and I drew out the H's.
Not seeing it, sir. Not seeing it.
Well,
huh?
Can you use, do you have a laser pointer or something?
All right, you see the laser pointer on this.
So we're not seeing what you're pointing on.
The laser pointer is on the Zoom. Is not when I touch it, it's not coming up on the screen. Let me, and okay. I can't write on this software.
All right, could you probably come out of sharing and then restart just to
Sure.
Okay, all right.
All right, tell you what, let me go back to the Zoom whiteboard.
We just keep our whiteboard.
This is CH4. I didn't hear that. Were you talking to me?
Yes, we're seeing now.
All right. This is CH4, same thing, showing the bonds between the carbon and the H's. So let's call the first one A and the second one B. Which one is A? Which one is B? Which one is condensed? Which one is displayed?
B is displayed.
B is displayed. Because it's one carbon, the first one is the same as the molecular formula. So the general molecular formula is the same as the molecular formula, which shows the actual number of atoms. You see that? When n equal 1. Tell me if you're okay with that. You're okay with that? Yes? All right. Let's go with n equal 2 now. N equal 2 now. Pay attention now and tell me if you're okay with n equal 2. You told me that when n equal 2, my general molecular formula, which come from CN, H2N plus 2, n equal 2 here, would give me, let me move this again. Wait, move. Come on, go away. Move this and move that. N equal 2 would give me C2H, H6, 2 times 2, 4 plus 2, 6, right? Yes, come on, talk to me. Don't let me move. So C2H, all right. So this is the molecular formula which came from the general molecular formula. Now, when I show the structural condensed and the structural displayed, you must show how the carbon atoms link to each other. So I can't write C2H6. This is just telling me that I have 2 carbons and 6 H's. So what I must do, I must say, all right, I have 2 carbons, I have 1 carbon, then I have another carbon. If it is condensed, I don't need to show the number of hydrogen. I just put 3 on this carbon and 3 on this carbon. And we call this the structural condense. Tell me if you're okay with that. All right, so I got it. All right. The displayed would simply now do the same thing, but just show the hydrogen bonds. That's all I'm doing. Is that better? So we have molecular formula, we have structural condensed formula, and we have structural displayed formula. How we stay? All right, let's do one more then. And I'm just choosing a number. Let's do 4. Let's do 4. So if n equal 4, sorry, let me use a different color. I'm sorry. I know sometimes you have difficulty with the red. Let's do n equal 4. So if n equal 4, we are still on alkanes. Then I have C, let me put molecular formula first. First one I want.
You have 2 instead of 4.
Oh, my brain tired, man. All right, I'm back. So it's C, so it's C4. H what?
8.
No, man, is alkane, you know, alkane.
9. 10, sorry. 10.
So 10. So what would be the structural condensed formula? So we can go C1, 2, 3, 4, and just put on your H's because you must have 4 bonds around each carbon. Remember, carbon is tetravalent. So 3 hydrogen and this one make 4 bond. So 1, 2, I need 2 more here. I need 2 more here, H's, and then I need 3 here. Tell me if you're okay with that, class. Yes, thank you. Thank you, Brittany. All right, so we're good with the structural condensed. Let's do the structural displayed now. Structural displayed formula. It will be now C, 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 and just show the H's. That's how we're doing. Good. Now, if we have, okay, she's asking why 10? Why 10? From the formula is CnH2n plus 2. If n is equal to 4, it's C4, let me move that, C4, H2 times 4, which is 8 plus 2, which becomes C4H. 2 4 is 8 plus 2, 10. That's why you must know the general molecular formula. Tell me if you're good now, please.
Sir, could you show us the page that was explaining the empirical, condensed, and other formulas, please, sir?
I soon come back to that. It's kind of hard to just, I soon come back to that, yeah?
Yes, sir.
You have a specific question you want to ask me before I go back there? Or you just want to see to take a picture of it?
I want to see to take a picture of it, sir.
I'll go back there shortly. Tell me if you're okay with alkanes. Who can name this alkane for me? Answer since you're on. What's the name of this alkane?
Butane.
Butane. Thank you. Why butane?
Because there are 4 carbons and 10 hydrogens.
So they're all single bonds, which means they're all alkanes. 4 carbons, but, and the ane is because they're all single bonds. Okay, and it follows the general molecular formula Cn.
For alkanes.
Yes. All right. Let me go back here for a second. So we're okay with the alkane part, right?
Yes, sir.
All right. So take this quickly. I will go to alkenes after. I hope you can hang on with me a little longer. Miss, we okay? Doc?
Yes, sir. We're fine.
Fine. All right. Good. I'm good enough. Just let me know if but I'm good.
All right.
So we continue then. All right. You okay
Hold
now?
on, sir. Hold on. All right. Good now, sir.
All right. So let me just go back to this thing for a second. All right, now, when I draw a molecule, tell me if you see it, all right? Can you see my screen? I'm on a software. Can you see?
Yes, sir.
All right, good. All right,
Yes, sir.
I'm going to remove what's on the screen. Delete that. And I'm going to draw 1, 2, 3. Who can name this to me? And tell me the type of formula is it? The type of formula it is. Is it displayed? Is it molecular? Is it condensed?
Hexane, and it's condensed.
Condensed.
All right, it's condensed. What's the name?
Hexane.
1, 2, 3, 4, 5, 6. Hexane. Good. All right. This one now. Let me go to this one and tell me what's going on with this one. What's going on with this one? Is that an alkane?
Alkene.
Alkene.
Why? Why is that an alkene?
It has a double bond.
Double bond.
All right. Thank you very much. The double bond is suggesting what?
Saturated. Unsaturated.
Unsaturated. All right. Good. I have that when I reach the actual reactions. Good. But good. All right. Now let's go to some structural displayed and so on for this one. Where is that thing again? Where is it? It's here. All right. So now we soon do some naming and isomers. Let me just do alkenes quickly. So again, same thing, prefix. Okay. Where are your alkenes? I'm coming back here. So look at those. Alkenes. Yeah, let's go here. No. Anyways, I can't find it. Let's go to the whiteboard. Alkenes. Same thing. So let's go with the general molecular formula, which is CnH2n. Let's go with the molecular formula. Then we'll go with the structural condensed formula, then the structural displayed formula. All right, give me one with 2. What's the molecular formula coming from the general molecular formula? One with 2.
C2H4.
C2H4. Give me the structural condensed formula. Tell me. C, then what?
H2.
All right.
CH.
All right. Let's write the next C first. So I have my two C's. It's an alkene. True? Which suggests what?
Add 2 more H.
A double bond. Yes. Is that clear? No.
Yes.
My H is no. So I could now say C. How many H's here? 2.
Or 2.
And 2. Do I satisfy my 4 bonds around my carbon?
Yes, sir.
All right. And now I can do this to show my structural display. How we stay?
Yes, sir.
Everybody all right so far? Quickly, give one with 5. When C is 5, what do I have for my molecular formula?
C5H10.
C5H10. Give me my structural condense. Let's go 1, 2, 3, 4, 5. Where do you want to put your double bond?
The first C?
The first one? Could I put it between the second and third?
Between, yes, sir.
Yes, sir.
I could put it anywhere I want. Not true.
Mm-hmm.
So let's put it here. This is what you might see. If I put it here, and the next time I put it here, then I am drawing a different structure with a different name. Not true?
Yes, sir.
Right. So if I put one here and then I put the double bond right here, now we're doing a topic called isomers. Okay, we're drawing the same. These are the two different structures, but they have the same molecular formula. You see it? Because I shift something. In this case, the double bond shift from the first and second to the second and third. So let's complete this one. So this should be CH2. CH what? 1, 2, so 2, 3, 4. 1, 2, 3. There's only one H. And then 1, 2 can come here. 2 can come here. And this is what? 3? 3, 4, 5, 6, 7, 8, 9, 10. Are we clear?
Yes, sir.
I would assume we can draw it out now. 1, 2, 3, 4, 5, and show the bonds. That's all. The bond between the carbon and the H's. That's all.
Excuse me, sir.
Your excuse.
What if you put the double bond at the beginning?
What is at the beginning? You mean in front here, sir?
In front, the first C. Yeah.
No, it can't be in front of the first C. It must be between 2 carbons.
Okay.
So when we name it now, right? You have 2 numbers where the double bond is on. It's on the first and the second carbon. Do you see that?
Yes.
The name must consist of the lower number. So this is not 1, 2, 3, 4, 5 butene. We don't use butene because you have isomers, right? So we can't just say butene. Where is the double bond? It's on the first carbon. Well, it's between the first and second, but the rule say you use the lower number.
So you have 5 carbons?
Oh, it's a 5?
Pence,
1, 2, 3, 4, 5. Yes. 1, 2, 3, 4, 5. Yes. Here we are. Third.
Pentene.
5. Huh?
You have butene, so change to pentene.
So put my thing here and put butene on it. What's going on? Somebody changing my writing, miss. I don't know what's going on.
No, sir. You wrote butene. We saw you. Sorry.
Yeah.
So you put pen.
I wrote it. I'm sorry. Hold on. All right. Let me change it quickly. I'm blaming people too for changing my writing. All right. All right. So this is pentene. Oh, I was saying you can't write pentene. So what you do now, I would name this, which we'll get to shortly. We'd say, so this is not good. Wrong. We'd say
1 pentene.
You can say 1 pentene, or the more appropriate way.
Pent 1 ene.
Yeah, 1 ene.
Tonian has a question.
Go ahead, Tonian.
Is structural formula the same as the structural displays formula?
The formula are the same. Structural condense and structural display are the same. The only difference is one shows the bonds between the carbon and the hydrogen, and the other does not?
No, no, I have a name for structural condensed formula. It's similar to one that I have. It's called the shorthand structural formula.
Shorthand structural formula for which one? For the condensed?
Yes, it looks similar.
Shorthand. Oh, it's really condensed. I'm not sure, but if you want to call it that, feel free. But do you see where it's condensed? You bring the things together. You see it? CH2 is brought in close to the carbon, while here they're out there showing the bonds. So that's why it's called condensed and the other is called displayed. You with me?
Yes, sir.
All right, that's fine. All right, so can I continue?
Yes, sir.
All right, I don't want to go on and they tell me say I need to go back, so let me know if I should go back or what. All right, let's go back up here for a second. So we just did alkanes and alkenes. Let me just run through alcohols and carboxylic acids for same condense and so on, and then we can go to the reactions. All right, let's go back to the whiteboard. Alcohols, CN. Let's write alcohols. Let me extend this thing here. All right, so CnH2n plus 1 OH for alcohols. Let's go with a molecular formula. So let's go with molecular formula. Let's go with a structural condensed formula, then the structural displayed formula. Talk to me. Let's give me 2, n equal 2.
C2.
C2.
H3OH.
H. 3. 2 times 2 is 4 plus 1.
Yeah. 5.
5.
Right. H5 and then OH.
OH.
Right. The molecular formula should really be C2H6O because it's just showing you the number of molecules present in the number of atoms present in the molecule. Clear? So this is really the molecular formula. All right. But that's fine. Let's go. What is this structural displayed now? I'm going to go condense. Then C, then OH. Then put in, how many H's around this one? Hello?
3. 3, sir.
How many around this one?
2. 2.
Good. And I have my OH there, which is my functional group. So you can see I have 2 H's, 2 carbons, 5 H's here, then the OH. Then my structural displayed is just going C, C, OH, and I just show my bonds. How we stay?
Good, sir.
All right, let's go alkanoic acid now, which is the carboxylic acid. Formula CnH2n. Oh, before I do that, class, let me give you one with 3 and show you that when I reach isomers, in this one, the OH can be on the first carbon, and in this one, the OH can be on the second carbon. Both names are different. So this would be propan 1-ol, while this would be propan 2-ol. So these are 2 isomers because the structure is different. Okay, so I'll give you some more examples of this later on. So CnH2n plus 1COOH. Give me the molecular formula for n equal 3. N equal 3.
C3H7COOH is in the chat.
C2H6.
All right. So, thank you. C2H6. Sorry, two
So,
twos.
sir, probably you should have said not N equal 3, but carbon. If you is it the number of carbons you want or not?
Already, man, N equal 3 is the number of carbon, but this carbon is to be taken into consideration. So when I say N equal 3, that's why they start with N equal 2 here. That's fine. You get me? That's fine. So C2 is fine because the one of the carbon is already in the functional group. So this is okay. But give me the H now. H what? 2 times 2 is 4 plus 1 or 5?
5.
Not 6, 5. All right. Then now COOH. We're good? So this really should be C3, for the molecular formula, C3H6O2. Tell me if you're seeing that.
Yes.
All right. Give me the structural condense. Oops. So we go what? For the condensed one, we go 1, 2, 3. Right? So CH3, CH2, right? We have 5, 2 carbons, 5 H's, then COOH. And then now we show it out. We go 1, 2, 3. This is your CO and the OH there. That's your H, 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 H. How we stay? How is that?
No responses yet. Okay, somebody says good.
All right. So I'm going to move on now, because we don't want to spend too much time here. So moving on. So now we understand that. We can move on. So we know now how to write our alkanes, alkenes, alcohols, and so on. Let's go to isomers. All right, let me show you this first. For alkanes, the first 4, 1, 2, 3, 4, these are gases. The others up to 10 are liquids. So you should know this. That's for alkanes. We're good? Can I go?
Yes. Yes, sir.
All right. Let me show you for alkenes now which ones are gases and which ones are liquids. So from C2 to C4 are gases, 5 up liquids. Remember, we don't have C1 when it comes on to alkenes.
I'm not sure if somebody wants to take a pick. They were saying wait.
For the first one, that's why I asked, for the first one, I asked you, okay, I'm waiting, I'm waiting for you to tell me when to go.
So they answered late.
Oh,
go ahead, Tonian.
Go back while they.
Before you go on, sir, what is the relative molecular formula?
Well, it should be relative molecular mass. When you add up the mass numbers, like methane, carbon is 12 plus 4, 16.
Okay.
When you add up the mass numbers, right? So the heavier they are, the higher the intermolecular forces, hence the higher the boiling point. All right, I'm going back to alkenes again. Then I go to isomers and those stuff. So here. All right, we have that now?
Yes, you can go ahead.
All right, now class, let's go back now to look at how we name these things now. All right, we have something called branch chains. So how do we know our branch chains? Look at this and tell me if you have any branches in any of the compounds on your screen.
Yes, sir.
Which one would you consider to be a branch?
The fourth one and the second.
Say the fourth one only.
The fourth one only? All right, we don't have any branches on anything. This is not a branch. And these are not branches. Not a branch, not a branch. Okay? When you look at these things and you name them, the parent chain is the longest continuous chain. Let me think of it as a road. Think of a branch as a road. And you have the main road and you have off roads, or, you know, what do you call those off roads? So this road would branch out from the main road. To be a branch, you can't be just a corner. You follow? This should be a corner. The road ends, but it turns like that. This is not a branch. So no branch here. This one would be a branch. To be a branch, you must be a carbon. Let me put a different color so you can see the branch. The carbon is on a carbon in between two other carbons. Do you see that? So the branch, this is the branch. Got it?
Yes, sir.
All right, that's a branch. Let's go back to the presentation. So no branches here. We only have continuous chains. So this chain, this carbon is 1, 2, 3, 4, 5. They're all single bonds. So it's pentane. They're all pentane. Not pent 1, this, not pent 2, nothing. They're all pentane. One continuous chain. Let me explain to you how you get branches now, and how you name your branches. Let me go to the simplest one now for the branches. This is, why red keep coming up? Come off, red. Hold on. This is let's go with methane first. So it's only one, so you can't think of any branches. Let me go with that one that is more than, oh, that's methane. So this is your alkane. Your branch now, right, is an alkyl group. Alkyl group. So where you have ANE, remove the ANE and add YL. The branch will always have one less carbon. So this is methane. The branch is methyl. If I have ethane, I have all carbons around ethane, all my 6 carbons. Then my alkyl group must have one less H.
Hydrogens.
Huh? One less H. Yeah, these are hydrogens, yes. So I have all my H's in ethane now. But now I have ethyl because I have one less H. This part that is missing, where are you? The part that is missing is where you're going to put it onto the main chain. Is that clear? So let's go 1, 2, 3. The branch now would be this, CH3. Do you see that? You see the branch, class?
Sorry, so the alkyl, it will always go in between the 2 carbons?
It must be on a carbon in between 2 carbons to be a branch. Yes.
Okay.
Oh, look here now though. Look here, however, look. Do not consider just this straight chain as the parent and this as the branch. You with me?
Yes, sir.
Because this could be my parent, and this could now be the branch. Blue. This could now be the branch. You see it? So you have to look for the longest continuous chain and then see which one is a branch. Are you okay with that so far?
Okay.
All right, look at this now. Look at this. 1, 2, 3, 4, 5, 6. Put a branch here. That's a branch. Which side do I number from? Do I number from this side? From the left or from the right?
From the right.
From the right.
All right. So you always start with the lower number closest to where the branch is. So that's 1, that's 2, that's 3, that's 4, that's 5, that's 6. Tell me if you're all okay with that.
Yes,
Yes,
sir.
sir.
All right. So the number, you must tell me the number where the branch is on. This branch, give me a second. Let me go talk to your dog here. 1 second. 1 second. Sorry about that. Where was I? The branch, right?
The numbering.
So, right. So this is the on the second carbon. So you must tell me the number of carbon the branch is on. First thing. What's the name of the branch? It's a methyl branch. What number of carbon is it on? The second carbon. Hence, the name now would be, let me move this quickly, 2-methyl, and then the parent. The parent comes last. So it's 2. Now, look here, people. Number and letter hyphen. So 2-methyl, okay? 2-methyl, parent is what? 6-hexane. Tell me if you're okay with that. Oh,
okay, sir.
All right. 2-methyl-hexane. All right, let's go back to the presentation. Organic chemistry is something you can't rush. It won't make any sense if you rush it.
Somebody say if you repeat.
Yes.
Repeat what? The name?
The process.
All right, the process. Hold on 1 second.
Go back to the whiteboard that you had to show.
I'm going back for a second, but take this picture. So you can look at it when I'm discussing it. Find and name the longest continuous chain. Tell me if you have that. Tell me if you have the picture.
Yes, sir.
Yes, sir.
All right, so let's go back here now. We were here. So we'll find the longest continuous chain. You see that? And it is 6, so hex. Then we are going to identify any groups attached to this chain. Do we have a group attached to it? You remember?
Yes, sir.
It was 6 carbon and we had a methyl group attached to it. Where is the methyl group? Which carbon is it on? You remember?
The second one?
Second carbon.
Second carbon, good. Second carbon. So you must indicate the position. So we number the chain already. We must now indicate the position of the substituent group, which is the branch, by an appropriate number. That's your 2. Okay? If it's only 1, we just say 2-methyl something. If it's 2, I'm going to give you one with 2, and then we talk about the prefix. Let's go back to where we were. Where is it? Oh, here. So 2-methyl-hexane. Tell me if you're all right with that so far. So the parent is hexane. We identify the parent, hexane. We identify that we have a branch, and the branch is on the second carbon. So when you name it, you tell us which group, which carbon the branch is on, and the parent comes last in the name. Are you okay with that?
Yes, sir.
All right. Look here now. Let me hear you now. Look, name this to me quickly. 1, 2, 3. Remember, when you do these things, always put on your H's. It's just because of time why I'm leaving them off. Who can name this one for me, please?
2-propane.
2 who?
2-methyl Sorry.
2,
1, 2, 3.
2.
Butane.
Propane.
Propane. Good. All right. Let me erase this and you give me another name. All right, that's good. Name this one for me now. 1, 2, 3. Branch.
2,2-methyl propane.
Dimethyl.
All right.
2-dimethyl.
No, you said, I heard 2,2-methyl. Let me hear 2-dimethyl. Good attempt. But guess what? You must tell me the number carbon the branch is on. So you can't just say 2,2-methyl. Let's go. You said, all right, so this is the parent. Let's call this a parent. 1, 2, 3. So it's propane. So parent, longest chain is propane. Are we okay with that?
Yes, sir.
We have 2 branches. One on the second carbon. And we have another one also, and put also on the second carbon. There are 2 of them and they are the same. So we use di for 2. So it's 2, number and number, comma, 2, comma, 2, hyphen, letter, dimethyl propane. Tell me if you're okay with that.
Yes, sir.
All right, everybody okay with that?
Yes, sir.
All right, let's go. Let's look at some questions now then. Questions time. Question time. Questions, where are you? Come. All right, not you. Name A, B, C, D as quickly as you can.
Somebody's asking if you always count from the right.
You count from, you can count from any side as long as the branch is closest to that side.
Sir, 2.
Wait. Let me just make sure everybody are okay with that. Tell me if they're okay with that, Doc.
Not well. Somebody's saying counting from the side with double bond. Just go over that number.
The one before, or the one I'm on now? The one before?
You can demonstrate with the one you're on, just to pinpoint how you number.
All right. So look now. Let's come here. Class. Which side is the branch closest? Is it to the left or to the right?
The right.
So we have to number from this side. So 1, let me use it so you can see it. So 1, 2, 3, 4. How many branch groups do I have?
2.
And both of them on the second carbon. True?
2.
Yes.
So it's 2, 2 dimethyl. What's the parent?
Butane.
All right, butane. Everybody okay with that? Tell me.
Yes, sir.
Yes,
All right.
sir.
Seeing the correct answers in the chat. Good. Look at B now. Whenever you have a halogen attached to your name, to your parent, it becomes bromo. So if you have chlorine, it's chloro, Br, bromo, iodine, iodo. The parent must be, if the parent chain with an alkene, you must have the carbon-carbon double bond a part of the parent. And you would start with 1, 2, 3, 4. So the Br is on the 4th carbon because you have to start with where the double bond is. Now, which carbon, what number am I going to use in this name? Is it 1 or 2 for the alkene?
1.
1. The 2, we use the lower number, so we use 1. Clear? All right. What number is the bromine? It's like the bromine is behaving like a branch. It's not really a branch, but it's behaving like a branch. So what carbon is it on?
4.
All right. So the parent must be the last name. So what do I start with?
Bromo.
All right. So 4. Bromo. What?
Butene.
Bute?
Teen.
Bute 1-ene.
Bute 1-ene, because I can have bute 2-ene, not true? Bute 2-ene is possible. So you have to tell me what carbon the double bond is between. It's between the first and second, but we go with the lower number. So 4 bromo, bute 1-ene. Tell me if you're okay with that. Doc, everything fine?
Somebody's not familiar. Probably they're just not familiar with how you name the alkenes.
All right.
So just repeat the naming with the double bond.
All right. When it comes to carbon double bonds, okay? 1, let me use 5. 1, 2, 3, 4, 5. I have 1 there and 2. So the double bond is between the first and second carbon. you must use the lower number in the name. So this is not 1, 2, 3, 4, 5. It's not pentene. It's pent-1-ene. You could have 1 pentene. Some people say 1 pentene. Okay. But the more encouraged answer would be pent-1-ene. All right. At the 6th form level, we accept pent-1-ene more than 1 pentene. I mean, it's not wrong, but I don't know.
You can show how you can now get pent-2-ene so that they can.
Yeah, man, I'm going to pent-2-ene now. So I'll go 1, 2, 3, 4, 5. That's 1, 2. So now it's between the 2nd and the 3rd carbon, but we always use the lower number in the name. So it becomes now pent-2-ene or 2-pentene. Tell me if you're okay with that.
Sir.
Tony-Ann?
I'm not sure what you're saying there, sir.
All right. All right. Look here. Where's the double bond here? I can't. You must start number. It's like a branch. You start number from the side closest to where the double bond is. So you have to start with 1, 2, 3, 4, 5. Here is 1, 2, 3, 4, 5. You agree with that? Tell me if you're okay with that, with the numbering.
Oh, yes.
All right. The carbon is between, the double bond is between the 1st and 2nd carbon, but you can't use the 2 numbers in the name. The IUPAC system, so you must use the lower number. So we have 2 numbers. What are those 2 numbers we have here? Here, where the double bond is. What are the 2 numbers?
1 and 2.
1 and 2. Which one are you going to use in the name? The 1 or the 2?
2.
Huh?
1, sir.
Yes, the lower number. So if you have 2 and 3, you use 2. If you have 5 and 6, use 5. If you have 10 and 11, use 10. In the name, you always use the lower number. That is the IUPAC system, International Union of Pure and Applied Chemistry. They give you the rules to use. Clear? You with me so far?
Yes, sir.
So the alkene must be a part of the main chain. That is why here, this is the main chain, and I started numbering from the alkene 1, 2. That means that the Br is behaving like a branch, and it's on the 4th carbon. So the parent is my alkene, which is the last part of my name. You see it? This one. Are you seeing it? Who was answering me a while ago? What's her name?
Tony-Ann?
Sir, where's the double bond, sir?
This one. I'm looking at this structure. B.
Yes, sir.
So it's between the 1 and 2. So the parent comes last in the name. You see it? And the branch now would be the bromine, which is bromo. And it's on the 4th carbon. Hence, 4-bromo, but-1-ene.
Sir?
Yes.
For the naming, could you put the pent-1-ene? I think somebody got confused with the 1 pentene different from the pent-2-ene.
Oh.
When you're differentiating, so just put pent-1-ene so that they can see the difference.
I was saying here, I prefer if you use pent-1-ene than 1 pentene. So this would be pent-1-ene. I mean, I don't think you'll get it wrong if you write 1 pentene, you know. I don't think they'll give it wrong, but this is preferred. You okay now? So we're okay with A and B. Yes or no?
Sir, I'm trying to get it, sir.
Yeah, man, that's fine. Just tell me which part you don't get. Tell me.
The B, sir, with the that part, sir, that we're doing. Oh, the bromobutene.
Bromine is the element. When it's attached to your carbon chain, it becomes bromo.
Yes, bromo.
So halogen. So if you have chlorine, it becomes chloro. If you have iodine, it becomes iodo. Fluorine becomes fluoro. You okay with that?
Yes, sir. But sir, I don't. How is it a double bond if C is not?
It's bromine is not a double bond. See double bond up here, sir? Between see double bond between the first and second carbon. You know, see it.
But
All right.
where's the chain? Where's the chain?
B.
Yes.
You see B?
Yes, sir. I'm seeing.
All right. So B. All right. Let's put it as a H. Ignore the BR for now. Put it as a H. Do you see what name would you give this if the BR was a H? One, two, three, four. What name would you give it?
I'm not sure.
Somebody help her now. What name would you give this if the BR was a H?
Butene.
What name would you give this structure if the BR was a H?
So, sir, would it be 4
Somebody says
hydro?
butene.
And would you just take out the 4 and bromo?
No, wait. What type of compound is it? No BR. What type of compound is this? Is it an alkane, an alkene, or alcohol, or carboxylic acid?
Alkene.
Alkene. Where is it, Urban?
To the right.
First one on the left.
Between the first and second carbon? Some of the background very noisy.
All right, let me mute.
Yes.
Go ahead.
Mute the noise in the background. It's very noisy. People, just identify the type of compound. You say it's an alkene. Then identify where the double bond is. Where is the double bond?
It's to the right, sir.
To the right. Between which carbons?
The first.
Carbon 1 and 2.
So what name would you give it? How many carbons do you have?
4.
4. So it's bute. And I know where is the double bond? Between what? Which number are you going to use in the name?
1.
1.
So bute, 1 ene. You good?
Yes, sir.
So we identify the parent. Let me now put a branch there, which is really not a branch, but it's BR attached to the hydrocarbon. What number carbon is the BR on?
The 4th one.
So 4 bromo. Parent. You see it?
I think somebody is querying the rule about using the lower number and tell him that the position of the double bond would trump. Yeah.
The double
Sir,
bond is,
excuse me, sir.
yeah.
Sir, like something like this, we have the bromine. You start with the parents first.
No, the parent it comes last in the name. But I was explaining first. Remove the bromine first and just think of it as this. All right, let me go back here. Look at this. Let me give you something simple. Name this for me, please. Name this. Anybody, name this one for me, please.
Ethane.
Who?
Ethene.
Ethene. Do you need to number the carbons?
No, sir.
No, sir. Not the first one.
Because only 2 of them. So just ethene. All right. Ethene. Good. Look at this. 1, 2. H, Cl. Name this. Name this.
Propane.
Huh? What's the parent?
Propene.
This is not carbon, miss. This is Cl.
Ethene.
It's chlorine, not a carbon.
Somebody has 2 chloroethene.
All right, there's no need for any number because guess what? This is, all right, it's 1, 2, right? 1, 2, it could be 1, 2 because the double bond is between 2 carbons, right? So because it's 2 carbon, you just go with chloroethene. ethene. Okay? Because it's only 2 carbons. You follow?
Yes, sir.
So chlorine.
Sir.
Look at this now. 1, 2, 3. Double bond. Name this for me now. Name this.
Pro 1 in.
Prop 1E.
Prop 1 in.
Prop 1 in. If the double bond was shifted to this side, it would still be prop 1 in. So in the exam, you might just say propene because both will give you the same thing. Clear? But let's leave that prop 1 in. We're okay with that so far, right? Suppose I move this now and put Cl here. Name this for me now. Name this.
1 chloroprop 1 in.
Thank you very much.
Chloroprop
Yeah.
1 in.
1, all right. 1 chloro, because now I have 1, 2, this becomes 3. So the Cl is on the first carbon. So it's 1 chloro, prop 1 in. Are we okay so far with that? What's going on there?
Yes, yes, they're saying yes.
What's some just pop up a while ago?
I don't know. Not seen anything.
Yeah. All right, go on. So it's 1 chloropropene. All right. I'm gonna shift the Cl now. So that's H.
Taje, so me attack.
H. Remember your mic is on.
Mute.
H Cl H Cl H. Name this now. Name this.
3 chloro.
Thank you very much.
1.
Yes, propanine. Thank you very much. Or you could say propene, but propanine is fine. Prop 1-ene. Are we okay with that so far? Look at the two of them and tell me if you're okay with them.
Yes, sir.
All right. So notice the alkene takes preference to any group. Where the alkene is a part of the parent, and any other group will behave like a branch. Okay? But if I have an alkane and I put a Br group or Cl or any group, then the Br would take the preference now, and it will now be the number 1 carbon if it's just an alkane. Okay? So what would this be? Name this one now.
Bromopropene.
Propane. Yeah.
Yes.
Propane. Good. All right. Look now. Look again.
Brittany Gray has a question.
Go ahead.
Sure. For the one that you just erased, when you have chloropropene, something like that, why didn't you have like 1 chloropropene?
This one, because it's only 2 of them, only 2 carbons.
Oh.
So Cl here. Well, yeah, I should have 1. 1 should be there for real. Because 2 of them, and it's on this one.
Okay.
And so this will be the first carbon. So yes. So 1 chloropropene. You're correct.
Okay.
Thanks for that. All right, go ahead and give me the name of this one. This one now. Look at this one. You give me this one. Give me this one.
2 bromopropene. Propane, sorry.
2 bromopropane. Thank you very much. So you see 1 bromopropane and 2 bromopropane. Now, do I have 3 carbons? Do I have 7 H's and 1 Br in both? This one?
Yes, sir.
And this one. Hence the term isomers. Okay? Take a picture of this before I go to that term, isomers, to show you something. And then we're going to finish up with some questions. I won't be able to get to the reactions today, but I guess next time
Yes, sir.
You see, with organic chemistry, you can't rush it, you know. I can't just finish to say I finish, and people don't understand. So we have to take our time. So that's chemistry for you. Can I go to the isomers now? All right, I guess that's yes. All right. No, class. The term in the exam, they'll say what is structural isomers, or they'll say what is structural isomerism. I normally tell my students, if you see isomers, you say these are. If you see isomerism, it is the existence of. Let me say it again. What are structural isomers? These are compounds or molecules with the same molecular formula, but different structural formula. What are structural, or what is structural isomerism? It is the existence of compounds or molecules with the same molecular formula, but different structural formula. It's the same thing, I just change the wording at the front. So it's like one is isomers are, the isomerism, if they ask the question, what is structural isomerism? It is the existence of. Tell me if you're okay with that.
Okay.
All right. So just in case you see you don't go crazy. So if you have 1, 2, 3 butane, and they say write a structural isomer of butane, you just simply shift one of the carbon groups and make it into a branch. That's how you get your isomers. If you have an alkene, you can shift the double bond group, or you can make a branch from the straight chain. How that sound? Tell me if we're okay. We're soon finished, man. Tell me if we're okay. Let me just finish off the introduction part.
Repeat.
All right, repeat. All right, let me go here, because I know when you see things, you understand it better than me just talking about it. So let me come here. So let me finish 20 slides already. Ooh. All right. Look here, class. So what I give you, C4H8. Alkene or alkanes?
Alkene.
Alkene. All right. C4H10. Alkene or alkane?
Alkene.
Alkane. All right.
Okay.
No, this one is ANE. This one is ENE. The top one is ENE. The bottom one is ANE. Alkane. And the top one is ene. So let's do some isomers. 1, 2, 3, 4. I'm at fact. Let me do 5. Let me do 5 to show you something. Let me just do 5 and done. Give me 1 second. Give me 1 second, class. 5. Where are you? So C5, if it's an alkene, it would be C5H10. And if it's an alkane, it should be C5H12. Tell me if you're okay with that. You okay with that, with this one?
Yeah.
All right.
Yes, sir.
All right. This time. Yes. Echoing. Yes. So 1, 2, 3, 4, 5. So this would be one of the structure. So I have 5 carbons, 10 H's. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Another one would be 1, 2, 3, 4, 5. So I shift the double bond to there. So it's now it was on 1 and 2. Now it's on 2 and 3. You see it?
Yes, sir.
Can I shift the double bond again? Yes or no?
No,
yes.
sir.
Yes.
No, I can't shift it, because look here. If I shift it 1, 2, 3, 4, 5, and I put it here, right? So it's here. Isn't it 1, 2, 3? So it's the same thing as this one. You see it? You see it? So these two are the same. So this one would not be an isomer of this. It's the same. So now I can go to branches now. So I could go back to the first one and make this one into a branch. Put it on the first carbon. So I could go now 1, 2, 3, 4, and make this a branch right there. So I have my parent with a branch. Same parent, I could put the other one here, right? So 1, 2, 3, 4. The branch come right there. So now, Miss, I think everybody tired now, Miss. I don't think. I think them.
Yes, I think overload is taking over. Right.
So what we can do is organize another time, and we can complete this and complete the other reactions, and maybe get into polymerization. Because I think it is. My voice.
Yes, sir. Any questions, students? If there's any aspect that you are not clear on, now is the time to ask your questions.
Sir, could you repeat the meaning for isomers and isomerism?
Molecules are atoms with the same molecular formula, but different structural formula. Or you can say that they different arrangement of carbon atoms. Understood? Question from Tony. Question from Tony.
Yes, you can unmute her. Yeah, go ahead.
What are the chloro and bromo? Chloro and bromo, what are those called?
They are halogens. They are halogens, but once they're attached to a carbon chain, they become bromo. The name change to a bromo or chloro or iodo. But they are halogens attached to your hydrocarbons.
Oh, so those are group 7.
Yes, group 7 elements. Yeah.
All right. So so persons are asking when will they know? So if you were having a second session, we'll email those who I have the email addresses for, or email your teachers. Recordings will be sent as well. Please remember that this was streamed on YouTube, so you can always go back to check it. MOE Jamaica YouTube channel. All right, so let us say thank you to Mr. Burrell, who took us through this session. It was a mammoth task. So let me see you go ahead and show your appreciation to Mr. Burrell for being with us today. All right. All right, good. I'm not seeing enough thank yous, man. We're getting back if you don't tell him how much you appreciate it, you know.
No, man, I'll be back.
I'm joking.
I'll be back to you, no matter.
Yes, we know it was a lot. And
yeah,
of course, he hasn't even touched the meat of the matter yet to get into reactions of these different organic compounds. But we thank you. We appreciate all that you have done with us today. And as mentioned, we will indicate if we're having a second session so you can tune in. Remember, day 1 and 2 will be on the YouTube channel as well. All right. Thank you. Any last words, Mr. Burrell?
Yes, it was a pleasure to be here to share with you, ladies and gentlemen, and colleagues. And I hope it was helpful. And I hope to continue to help you in any way I can. So next time we meet, we will continue with the lessons. Thank you.
Okay, blessings to all. All right, thank you everyone for tuning in. All right. They're telling you to start back at branches when you start again.
No problem. No problem.
All right, blessings. All right.
Take care.
Take care. Okay, bye everyone.
Bye.
Okay.
Bye, Miss. Thank you.
No problem. You're welcome.
Bye, Doc. Take care. Bye, everyone.
Yes, sir. Thanks again, Sir Burrell. Blessings. All right.
No problem. No problem.
All right, Sir Burrell. All right, and thank you, Miss also. Have a good evening.
Yes, you too. Thanks to everyone. You're welcome. All right, bye.